Hello guys, today we are going to see about how the Internet of Things being effective for being used by the electric vehicle charging. So this topic is being referred from Oliver Hudson, Omar Elomi and David Boschwatik, the Internet of Things application to smart grid and building automation while a publication 2012. So, charging standard overview. Until 2010, the standardization of EV charging is addressed only a very basic aspect, such as how the vehicle should behave when it detects a charging power or go back to sleeping mode when the charging power disappears. There are different varieties of plugs available. So, the below figure shows that many case EV plug. So it is a 1, 2, 3, 4, 5, 6, 7. It is a 7-point connector. So which is a standard connectors has been started developing and certain standardized thing being evolved. So here, before going to see how the EV is connected with the IoT, we must know the basic things of EV charging. So EV vehicle charging. So here we're not going to see about the electric vehicle manufacturing kind of thing. We're just going to see during the charging time, during the charging, how the information is being transferred to the charging dock. So before that, we are going to see about the two standard EV side connectors, the Type 1 connector and Type 2 connectors. So, as like the micro USB, that is micro USB and mini USB, Type 2, Type C, such kind of things. Similarly, for the EV electric vehicle, so these type of connectors are available. The Type 1 connector, which is simply a J1772 SAE type single phase connector with 5 pins, a charging voltage of up to 250 volt and a charging current up to 32 amps. That is AC charging up to 7 kilowatt. The full charge is in 4 to 6 hours or 50 to 70 kilometer per hour of charge. The Type 2 connector originally proposed by Minikis, which you see in our left side of the slide, which enable a singular three-phase charging with charging voltage of up to 500 volt and a charging current up to 63 ampere. The 70 ampere for single phase charging, the three-phase voltage, three-phase 400 volt charging at 32 amps represent the charging power of 22 kilowatts. The full charge in couple of hours are 100 to 150 kilometer per hour of charge. Further, we are going to see about the charging standard overview. In Europe, as of May 2011, the proposal of EV plug alliance developed called Type 3 plug has been developed. At the international level, the current standardization converged so far only on the requirement of IEC 62193-1 2003 plugs, the socket outlet vehicle coupler, and a vehicle inlets conductive charging of electric vehicles. The part 1 of this says the charging of electrical vehicles up to 250 amperes AC and 400 ampere DC. The pictures here, the three different pictures shows the first is a type of a connector that is called as IEC 60309-2, the 3P, that is a three-phase neutral earth 9H plug, and the second middle one is SAE J1772 plug, which is being widely used nowadays car. Present car, the Type 3 plug on the first EV plug alliance, that is it will be in the charging station. So this is about the Type 3 plug. In IEC standards, the part 1 says the charging of electrical vehicles, the enhanced security. The early EV chargers relied only on traditional 30 milliampere differential circuit breaker to detect the current leakage. The modern EV chargers must have a dedicated pilot wire which conforms to IEC 61851 2010 electric vehicle conductive charging system of part 1 general requirement, which implement the proactive mass defect detection. This enhanced security mechanism is detailed in IEC 61851 pilot wire. The next one is basic charging power control by the charging infrastructure. IEC 61851-2010 also specifies a simple pulse width modulation protocol on the pilot wire, enabling the EV charging equipment, that is the EV SE, to communicate with the EV, the maximum charging current allowed. The initial idea was to make sure that the EV would never draw excessive current capable of causing the fire in the charging infrastructure. But the mechanism also be used for admission control and demand response. The bidirectional charging control, that is the DC charging, the functional area covers also the communication by the EV to EVSC, that is the EV charging equipment related to the charging of EV battery by external CC charger, like the constant current, constant power, or a constant tension required depending on the battery technology. There are no agreed international standard yet at the level of IEC 61851-23 was published as of March 2011. The de facto standard for existing vehicles is CHAdeMO, which uses the dedicated pins on the J1772 connector, which you have seen in the previous slide. The high-level communication. The functional area encompasses the requirement of charging control but covers the security, charging, and potentially many other services. At the international level, there are two standardization tracks, the ZigBee SCP 2.0 and IEC 15118, that is a road vehicle to grid communication interface. At the physical level, the proposal are to use the IP version 6 on top of the home plug green PHY G3 translated to 150 to 450 kHz frequency band or a CAN CHAdeMO proposal. IEC standard related to EV charging. The main IEC standard related to EV charging is IEC 61851, managed by IEC TC 69. The IEC 61851 is split into several documents. The Part 1 describes the general requirement, the Part 21 describes the electric vehicle requirements, the Part 22 describes the AC charging station requirement, the Part 23 describes the DC charging station requirements, and Part 24 describes the communication protocols. The IEC documents three cases for physical connection: case A, case B, case C. The case A, the cable and plugs are attached to EV. Case B, the cable is detachable. In case B1, the cable connects to the standard domestic plug. In case B2, the cable connects to the specific charging station. In practice, EVs sold in 2011 usually include a B1 cable by default. The B1 cable connects to the standard domestic plug. The case C, the cable is attached to EVSC. The IEC also defines several charging modes. The nomenclature is now used by all EVSC vendors. The mode 1 uses a standard 16 ampere socket outlet, single phase or three phase. The protection against electric shock relies only on differential breaker in the charging infrastructure or in the cable. The charging mode is prohibited in the US, but outside of the US, most EV currently circulating use mode 1 charging, and mode 1 charging is still proposed by default as many of new EVs in 2011. So mode 2 still uses the 16 ampere or 32 ampere socket outlet on the charging infrastructure side, but uses a specific plug on EV side. The cable must include a protection device that implements the proactive current leakage detection through the pilot wire system. The additional PWM communication over the pilot wire remains optional. This mode is the default for the newer EV in the US and Japan, and is available as an optional cable for most recent EVs in other countries. Mode 3 requires a dedicated EVSC. The pilot wire that controls the charging station is managed by EVSC. No charging power is available over the charging cable until the EV has detected by the pilot wire and the absence of current leaks or the ground defects has been verified. The pilot wire also optionally indicates the maximum charge level by using the PWM modulation 16 ampere normal, 32 ampere semi-fast and 32 ampere fast. Mode 3 is safer than mode 1 or 2 because the plug is energized only if all the following conditions are made. The vehicle power the vehicle power plug is totally inserted. The pilot pin is last to connect. The ground continuity has been checked. The pilot wire present. The vehicle has transmitted a signal confirming that everything is secure and the charging is ready to begin. The mode 4 applies to the external chargers, example DC charging, and also covers the inverse mode when the EV providers power to the charging infrastructure. This mode, covered by IEC 61851-23, was not fully specified as on March 2011. It requires a serial bidirectional communication over the pilot wire. The left side picture shows of standard of J1772 Type 1 connector on a Renault electric vehicle. Here, the right side picture shows how the pilot wire is circuited according to IEC 61851 and J1772. So you are seeing the vehicle and EVSC, that is a charging dock. So the duty cycle, that is a pilot wire, is connected to the vehicle and EVSC is connecting, and when the circuit is complete, that is by satisfying the condition what they have mentioned in the previous slide, such as leakage current and ground connectors are being properly connected, the vehicle starts, the EVSC start charging the vehicle battery. In the new version, the mandatory EVSC charging cable function for the charging modes of 2, 3, 4 are the verification that the EV is connected, the continuous control of the correct grounding of electric vehicle, energization and de-energization of the electric vehicle. The new optional functions are the selection of charging power, determination of ventilation requirement of charging area, bidirectional power control, not yet specified in the earlier edition of 2 IEC 61851. The high level communication. So what is the communication level? So the left side of the picture shows the overview of IEC 151182 charging session, a semi-online protocol flows. The right side indicates online protocol flows, that is a charging session online protocols follows. The charging cycle from the vehicle to EVSC and to the provider, so who is actually the owner of the particular charging dock, what kind of information has to be transferred about what are the vehicles are being transmitted, because we need to record everything, right? If a person, we cannot give it for a free, or we cannot give it for the strangers to charging of any vehicle, so that it may defect the charging station also. So the connection is established. So TLS session is establishment, the exchange of security related information such as CRL updates, EVSE certificate, the service discovery, the power discovery and delivery. So exchange to the provider, what we are going to exchange to the provider, the security information, CRL updates, certificates about the particular vehicles. The meter reading for the charging period will started. The signed meter reading will get started. So the meter reading for the charging after completion of charging, the charging cycle, the total meter reading will be shown, and the charging finished measures will be transmitted to the vehicle. The connection termination will be made, and then exchange of signed charging records via network of online. That is the semi-online protocol says. On the right side, it is a completely online protocol, because this is based on a standard charging connectors. So the more number of connection will be made, and there will be a certificates for a token will be transmitted from the charging station to the provider will be made. First, the exchange of service information such as CRL update certificates, as like what you see in the previous semi-online method. The connection is established, TLS session establishment, exchange of security related information, service discovery, charging requirement data will be transmitted. So what type of charging requirement is needed, how long you need to charge. You need a fast charge, it will be at the rate of different level, and you need a medium charge, semi fast, and a low speed charge, how long you are going to charge, and what is your battery level. So everything will be transmitted, and then based on the scheme of transmitting the token from the service provider, whether the service provider accepted it, the accepted data will be transferred to the vehicle from EVSC, and then charging plan selection will be made by the vehicle. The charging plan will be selected and it is approved by the provider, and then charging cycle is being made. The last signed meter reading will be transmitted to the provider, and then connection is being terminated. So this right side is a completely online version that you can select able to you can able to select a certain ranges of charging methods, and the left side is a semi-online method. There is no ranges, just you will be charged for this much usage, this hour usage, this much of power. That's the standard one. Vehicle to grid protocol TP header structure will be like this. So the payload type, the data transmitted is a kind of XML format. So this is the actual data, the protocol version of 0xV2 GTP V1, the bit inverse protocol of 0xFE for V2 GTP. The payload length will be transmitted, and actual payload will be like this. The V2G, that is a vehicle to grid protocol session, is organized as follows. The initialization of the communication session, supported app protocol request response, session setup request response, the service discovery request response, and service selection payment request response, payment details request response, and contract authentication request. The charged vehicle setup is charging process. The charge parameter discovery request response will response a line lock request response, because in mid of the thing you cannot able to disconnect your vehicle from the charging dock. The power delivery request response and metering status request response, metering receipt request response. So tariff table will be developed, and tariff description will be maintained, and a tariff entry will be made. So each and every unit is as per the standard of IEC 15118, which is drafted on 2011. The charging process, how the process is being maintained, the charging profile, maximum power, what is the maximum power to be done. Everything is being recorded on IEC 15118 as per the May 2011 standard, and finalize the charging process. J1772 communication between the plug-in vehicles and utility grid. The left side picture shows that the supply system and what are the connectors says the pin 1, that is the L1 line, and a pin 2 is the L2 neutral. The pin 3 describes the ground, and pin 4 is a controlled pilot, and pin 5 is the proximity detection. So this is a single phase kind of a charging system. The three charge levels are there. The level 1 charges via charge cable, including the pilot wire control equipment connected to the US domestic plug, single phase, that is a 120 volt 15 to 20 ampere. The level 2 charging via fixed EVSE station connected to a 240 volt single phase up to 80 ampere. The current level is being um, more than the double kind of thing. The 20 amps to 80 ampere will be there. The DC charging using a off-board charger. J2293 specifies the Task Force J2293 of SAE is focused on standardization of EV and communication between the EV and EVSE. It initially addresses the both conductive and inductive charging, but inductive charging is no longer considered. The J1772 standard, which focuses on conductive charging, implements the same pilot wire mechanism as the IEC. The 2008 version of J22932 describes a high-level charging protocol based on the J1850 serial communication protocol, which has never really been used and was normally made to absolute in 2010. The SAE worked on comprehensive list of use cases for EV charging, published as J28361 in April 2010. The SAE then worked on the revised architecture and communication supporting all the use cases, and considered two options for high-level communication protocol: the CAN bus and IP version 6 and ZigBee. The CAN bus that is adopted in all modern vehicles but would need a specific message set to support EV charging. The IP version 6 and ZigBee SCP REST data model initially both 6LoW WPAN over 802.15.4 and IP version 6 over CPL were considered at present. It seems the SAE is focusing on IP version 6 over CPL. Mostly, most likely home plug green physics. The CAN bus. The proprietary protocol designed by Bosch GmbH in 1983, designed by Bosch GmbH in 1983. The CAN2 was published in 1991 and used as an expanded 29-bit identifier format. A half-duplex multi-master broadcast serial bus using NRZ encoding, non-return zero encoding. The CAN implementation rely on physical layer specified by ISO 893.2.2003, that is based on the Road Vehicle Controller Area Network, the Part 2 of High Speed Medium Access Unit, or ISO 11-893.52007, that is a Road Vehicle Control Area Network, and Part 5 of High Speed Medium Access Unit with the low power mode. The achievable bitrate varies between 1 megabyte per second, the distance up to 40 meter with ISO of 11.893.2 or 5, and 125 kilobits of distance up to 500 meter with ISO 11.893.8983. The CAN data link uses the ISO 11.893.12003, which specifies the medium access control sublayer and a logical link control sublayer. The MAC sublayer implements a CSMA, collision avoidance mechanism. All the messages begin with the ID, which also encodes the priority level in case of 1 and a 0 are simultaneously transmitted on the bus, but only value 0 will be sensed by all the nodes in the network. The node that had just transmitted as a 1 then knows a collision has been occurred and stop transmitting. The original CAN and CAN2 2A specification uses a 11-bit identifier field. On recent CAN 2.0 implementation using a 29-bit identifier structure, the first 3 bits are reserved for the priority levels and next 18-bit encodes the frame format and the last 8-bit encodes the sender address. The ID field is followed by the 8 payload byte. Any higher layer protocol must be used on the top of the CAN. For instance, the ISO transport protocol is used by the existing diagnostics protocol on CAN and provides a segmentation, flow control, broadcast and unicast addressing. The error recovery is left to the application layer. The TP 2.0 that has an automatic error recovery CAN open developed by Bosch and handed over to the CAN in automation user groups in 1995. It was standardized as a European Nation 50 2354 in 2002, which defines the object dictionary enabling the cross manufacturing compatibility. The SAE J1939, which defines a segmentation and flow control mechanism and an application layer for buses, trucks, and agriculture equipment. At present, there is no proposal to port 6-LoWPAN over CAN, which means the CAN option for EV to EV SC communication would not be IP based and would serve only for a low-level control purposes. This is considered as a problematic by some car manufacturer who believe the EV to EV SC connection may be leveraged also for other uses, for example, downloading movies while charging, and in general would require the versatility of IP. The CAN, which was designed for a closed system, also lack a set of specifications for a strong authentication and security which are required for communication between EV and EVSC. J2847, the new recommendation practice for high-level communication leveraging the ZigBee Smart Energy Profile. The J2847 series is the result of the joint work since 2009 between SAE and ZigBee and HomePlug alliances with the following objective: defining a message set that would support the requirement of J28361 integrated with the home area network and utility networks. The follow the REST model recommendation by the NIST and based on the IP version 6. The original ZigBee SCP 2.0 specifies does not addresses the EV charging use cases and only therefore the SAE reworked the specification and split it into the several documentation focused on the specific requirement for EV charging. The J2847 Part 1 describes the communication between the plug-in vehicles and utility grid. The Part 2 describes the communication between plug-in vehicles and the supply. The Part 3 will focus on reverse power flow, and Part 4 describes the focus on charging system and EV diagnostics, and Part 5 will focus on vendor specific extensions and options. The use cases and basic use cases over PHV, that is a partially hybrid electric vehicle 15 and 40 and BEV versions are the battery capacity in kilowatt hour is 5, 16, 24, and the charging time 20% to 100% for a different vehicle is specified here. A typical battery capacity and the charging time of electric vehicles is described. As a conclusion, I would like to represent the need for the communication system in cars goes much beyond EV charging. The potential for M2M service provider is enormous. There are about 50 million cars produced in the world each year for a total of over 600 million in circulation. The European eCall directive, which mandates the installation of automatic emergency calling in new cars as of 2014, has made it mandatory to install a cellular communication platform in all European cars. Building on this, most automakers are now planning to use this cellular communication platform to implement a M2M GPRS connection for maintenance and monitoring of vehicles. The such systems are already in place in all new electric vehicles and soon generalized to all new cars. So what is the next step? The automakers will soon provide an onboard IP connectivity for the car appliances. The GPS system, for instance, it would make no sense to build a separate vertical system for EV charging, car monitoring, and onboard M2M connectivity. Clearly, our vehicles will need to provide a generic M2M infrastructure able to leverage both cellular networks and IP connectivity provided through the charging station. With this in mind, we believe that protocols are defined currently will need to evolve. IEC 15118 current draft is too vertical, but explore in detail all the semantics for EV charging in the context of multi-actor deployment. The ZigBee SE 2.0 is a REST-based and a little more generic but still focused on energy management. The multi-actor interaction are not as clearly defined as IEC 15118. Thank you.